So we'll start the session with the discussion of mock paper 6, set 1. And after discussion of set 1, we'll discuss set 2 as well. So in the first question, we have a hydrated aluminum chloride was there. Is a white solid when it is heated strongly. Hydrated aluminum chloride produces steam, hydrogen chloride gas, and aluminum oxide. For those who just joined now, this is mock paper 6, set 1. You can use mic, chat, or screen annotation to answer the questions from this paper. And the hydrogen chloride gas is a toxic and aluminum oxide is a white solid. So a teacher heated a sample of a hydrated aluminum chloride here. And as a result, it give a hydrogen chloride gas, a steam is also produced and aluminum oxide is there. Name the item of apparatus label A. What we call this A? So that is a crucible. Some students wrote beaker, so you're not supposed to say beaker. It should be a crucible. Crucible, whenever we want to heat a solid in a deep container, we prefer a use of a crucible because it can allow, like, it can act as a furnace. That is another advantage of using a crucible. Explain why this experiment should be carried out in a fume cupboard. So actually answer is given in the question. Answer is given. Why it's not a beaker? Because you can see the size of a beaker. We don't have this much small beaker, and beaker is made up of a glass. Glass is not a good conductor of heat energy. Whenever we want to heat something for a very high temperature and trap the heat energy, we prefer the use of the crucible. So as you can see in the question, they mention here that it is a toxic gas. Hydrogen chloride is a toxic. So why this experiment should be carried out in a fume cupboard? So whenever a reaction is releasing any toxic gas or a toxic fumes, we always prefer the use of a fume. So from the experiment, you can identify the use, whether you have to use a fume cupboard or no. And whenever you see any toxic substances released, you should always prefer the use of a fume cupboard. Answer for A1, for those who just joined now, the answer for A1, that is a crucible. What is a crucible? Crucible is a container which we use to heat a solid. Whenever I want to remove the water of crystallization from the solid, whenever I want to heat a solid, we prefer the use of crucible. Not a beaker. Like some students wrote beaker as an answer, which is not at all acceptable. So it's not a beaker, it is a crucible. And the next part explain why this experiment should be carried out in a fume cupboard. So even the experiment it is written, the answer is written in the question that hydrogen chloride gas is a toxic. So as a hydrogen chloride gas is a toxic, so you have to just copy this statement here that hydrogen chloride gas is a toxic gas. That's why it should be carried out in a fume cupboard. Whenever any reaction releases a toxic gas, we prefer the use of a fume cupboard. What is the difference between evaporating dish and a crucible? Evaporating dish is having a large surface area, and whenever we want to remove the liquid from the mixture, we use evaporating. But here, a deep container, a crucible is there, a deep container mainly to trap the heat energy, and it temperature can rise to a very high like the heat energy which we supply can be trapped, and the temperature of a substance can be rises to a very high temperature. So that is the evaporating dish is having a large surface. If this was an evaporating dish, then how it should look like? It should look like this. But if it is a deep container, it is a crucible. Already you have the file related to paper 6 in which all the apparatus are listed. So go through that. The next is the hydrated aluminum chloride is to be heated very strongly. Describe how a Bunsen burner is adjusted to make a flame as hot as possible. When we want a hot flame, it means we want to burn it completely, like the combustion should be complete. So more holes of, yeah, because the same idea that when the air holes are open for a Bunsen burner, we have these air holes. When these air holes are open, so maximum amount of the oxygen will be there mixed with the gas, and as a result, there's a complete combustion. So for a Bunsen burner to give a very high flame, what we should do? We should open the air holes. So if you write here, open the air holes, that is fine. So air hole should be open so that maximum amount of oxygen mixed with the gas and a complete combustion take place. And if they ask us like how we reduce the flame, so we will write that we will close the air holes for a Bunsen burner. In part T, during the experiment, the mass of apparatus A and its content decreases. Explain why the mass decreases. As you can see, we were having an aluminum chloride. No, this is not the right answer. This is not at all correct because if a crucible melts, the whole apparatus will melt. What actually happened, even the answer is given in the question itself. So see this part of the question, they mention here that when you are heating hydrated aluminum chloride, it produces steam, hydrogen chloride, and aluminum oxide. Aluminum oxide is a solid. So that will not escape. But what will escape when you're supplying heat energy? The steam will escape as well as the hydrogen chloride gas. So one is the steam escaping, another one is a hydrogen chloride gas. So what is the answer here? Why the mass is decreasing during an experiment? Why the mass is decreasing? Because the hydrogen chloride gas and the steam, those are the contents of the apparatus A, not the apparatus. So no, that is a mass of apparatus A is decreasing. Like what is the apparatus A? Apparatus A consists of this compound. Apparatus A is what? Apparatus A is a crucible which contain a hydrated aluminum chloride. So when you supply the heat from the bottom, the hydrated aluminum chloride start to decompose, which release H2O, and it also releases steam because it's a hydrated, and it turned into aluminum oxide which is left behind. So why the mass is decreasing? It's not because the crucible is melting, because the substance which is inside the crucible, that is chemically changing and releasing the gas. So never, don't say a substance as apparatus melt. That is not at all practical way of answering the question. Is it clear why the mass of content A is decreasing? The next is describe what the teacher can do to make sure that hydrated aluminum chloride reacted. So heat until no change in the mass or no more mass change, or heat till the constant mass. Instead of saying no more gas is given off, The best way to answer such is until the mass does not change. Like what we will do, we will supply heat energy, we will heat it until the mass does not change. Like we have a hydrated aluminum chloride, we will heat, then we'll reweigh, then we'll supply heat energy and reweigh, and we'll heat until the mass does not change. So this will give the mark here that heat until the constant mass. So heat will give a mass, a mark here, and the mass does not change, give a mark. Because we are not testing the gas, so hydrogen chloride is a colorless, so it's hard to recognize that whether a gas is released or no. So when colorless gas is there, it is difficult thing to identify. That's why we cannot say that. In the second experiment, the teacher uses the apparatus in figure 1.2 and collect the water made. Hydrated aluminum chloride is heated and a water which is produced is condensed. Explain the purpose of the ice. Why the ice is used? So purpose of the ice is to condense the water. Sorry, condense the steam, I mean. Yeah, condense the steam, that's right. Or the water vapors, you can also say. So as this is giving us the hydrogen chloride gas and a steam, do we? You can use a mic as well if you want to, or you can use the chat. Do we have to mention what? No, any one you can mention. You can mention to condense the steam. You can mention, you can, no need for hydrogen chloride here. You just have to mention the water. Main marks are for water, H2O. If you write to change the gas into a liquid, that is more appropriate is here. Water is specifically you should use rather than only a journal answer like an, because definitely it is cooling down, so the gas will turn to liquid. But what it is doing, it is converting the steam into liquid. So state that the steam will convert into a liquid or a water, you can say that. Next is the water collected is not a pure. Describe a test a teacher can do to show that the water collected is not a pure. Whenever we want to check the purity of a substance, we should check the boiling point, like check the boiling point, and it should, if it is not a pure water, it will not boil at 100. If it's a pure water, the pure water will boil at 100. Yeah. So water does not boil exactly at 100. That's right. That's how we test to check. If they ask a chemical test to check the presence of the water, then we can mention anhydrous copper sulfate or anhydrous cobalt chloride. Any one of them we can mention. The next is related to titration. A student investigate the reaction between a hydrochloric acid and sodium hydroxide. The student does two experiments. So what he did in the first experiment, fill a burette with the aqueous sodium hydroxide. So there is a sodium hydroxide in a burette. And run some of the aqueous sodium hydroxide out of a burette so that level on the scale. So he removed some of the liquid and he record the initial burette reading. Using a measuring cylinder, he poured 25 cm cube. For a burette, 50 is at the bottom because it's all 0 is there at the top and 50 is there at the bottom because it shows us how much volume is removed from the burette. That's why 0 will be there on the top of the burette. Then using a measuring cylinder, he poured 25 cm cube of a hydrochloric acid. So he can use, he used a measuring cylinder, but appropriate, it should be a pipette, which can exactly measure 25 cm cube. And stand a conical flask on a white tile. What is the main reason of having a white tile or a white background? So that it is easy to observe the color change. Then add 5 drops of a methyl orange indicator. So in this one, he add a methyl orange. It's an acid. So what should be the original color of a solution because of the methyl orange in acidic condition? Original color. Methyl orange. No, it's a methyl orange. What is the original color of a methyl orange? Colorless is for phenolphthalein is colorless in acidic. So the original color,
Orange.
no, red is, it's red actually, orange for a methyl orange when the solution is neutral. So it's not orange, it is red because it is acid. In acid, methyl orange is red. In alkaline, the methyl orange is yellow. And in neutral solution, it will be orange. So what will the color change when we add this sodium hydroxide from the burette? The methyl orange will show a color change at the end point. It changes from red to orange. No, not red to yellow. We'll write here orange because orange is, it's a slightly alkaline, but we assume that it's a neutral solution. So don't write yellow. Yellow is when it is, when they say that it is alkaline solution. So in this case, it will be from red to orange. To remember methyl orange, the color in neutral solution to be orange. Okay. Then slowly add a sodium hydroxide and swirl the mixture until the solution changes the color and record the final burette reading. That is what we did in the experiment one. This was our experiment one. Then we empty the conical flask and we rinse with the distilled water. So when we empty the conical flask and we rinse with the distilled water, and then we refill the burette with the sodium hydroxide. So a burette is there, which is filled with the sodium hydroxide, NaOH. And we record the initial burette reading. We add, using a measuring cylinder, we pour 25 cm cube of a hydrochloric acid, HCl. But then what we did, we add 0.5 grams of a calcium carbonate. Now, what will happen? What is the effect of this adding 0.5 grams of a calcium carbonate? The calcium carbonate will react with an acid. So some of the acid will be reacted with calcium carbonate. So amount of a hydrochloric acid, the moles of the hydrochloric acid in the solution will decrease because acid can react with the carbonate. Then we add a methyl orange. Again, we add an indicator and then we add a sodium hydroxide from the burette. So definitely in experiment 2, we need less quantity as compared to experiment 1. Why? Because in experiment 2, some of the hydrochloric acid will react with the calcium carbonate. So remaining hydrochloric acid will react with the sodium hydroxide. That's why practically the quantity of a hydrochloric acid which is required for the second reaction will be lower than the first reaction. Then we have the burette readings are there. Use a burette diagram figure 2.1 and 2.2. Record in experiment 1 and 2. So initial burette reading. What is the initial burette reading? As you can see, the burette 0 is always on the top.
0.6.
0.6. And what is the final?
19.
19.2. And what is the change? The difference? 16.6. 18.6. Okay. So 18.6 is the difference in the burette reading. And same thing we'll do for the second experiment. It was, so the final burette reading for it was 19.2. This was, initial was how much? 0.6 and the difference was 18.6. And this is 1.5678 and so 6.2. So approximately, as you can see, like 18.6, it's the ratio. If we compare, it's like it look like 3:1, the ratio of the volume. So ratio of the moles also that shows it is 3:1. The next we have, as they asked, state the color change in a conical flask at the end point for both experiment. So initially you was having an acid, so that's why it should be red. And then what it will turn into, because it's an alkaline, a neutral solution, so orange. Okay. If it was originally alkaline solution, so we'll say yellow. Like let's say if the question was originally it was alkaline and then acid was added from the burette, then the color change will be from yellow to orange. Okay. So remember a methyl orange in a neutral solution to be orange in color. Now 0.5 grams of a calcium carbonate is added to a conical flask in experiment 2. A gas is produced. suggests the identity of the gas. So if we add a carbonate, a metal carbonate to a hydroc
Carbon
acid, so the gas,
dioxide.
good. So gas will be a carbon dioxide. The next is experiment two. The conical flask is rinsed with the water, but not the burette. Is not rinsed with the water. State why there is no need to rinse the burette with the water. Look, why we did not, what we did, we were having like a conical flask. The conical flask was having a neutral solution. Then when we remove this, discard this, and we add a distilled water and we wash with the distilled water. But in case of a burette, as you can see, a burette is already containing sodium hydroxide. The same substance of a sodium hydroxide is there. So that's why if it is made up of a same, like if it is, we want to fill up with the same substance, then we don't have to rinse. We don't have to wash. So the simple answer for this question you will mention here, the burette is already filled with the sodium hydroxide. That's why we don't have, if there is no change in the substance filled present in the burette, that's why we don't have to wash with the distilled water. If we want to, let's say for the second experiment, we want to add a hydrochloric acid in the burette. So first what we should do, first we will wash with the distilled water and then we'll wash with the hydrochloric acid, the substance which we want to fill up. So the simple answer here, that it's the same substance is present in a burette. That's why we don't have to rinse with the distilled water. So explain why conical flask is rinsed with the water. Why we rinse a conical flask with the water? What is the reason for that? Because this conical flask was used in experiment one. So we want to remove the impurities from the experiment one. Yeah, content were changed. That's right. And the second thing is because we want to reuse it. So we want to remove impurities from the first experiment. So we want to remove impurities from the first experiment or experiment one. That's why we should rinse with the water. The conical flask is not dried after rinse with the water. State how drying a conical flask affect the water. If we dry or we don't dry, will it make a difference to the end point? The answer is no. It's not yes. No difference. Because water is not the reactant here. Look, what we did, let's say the first experiment, I will explain the answer. The first experiment, we took a conical flask and we carry out the experiment, like adding a sodium hydroxide from the burette, the NaOH, and the conical flask was filled with a hydrochloric acid and we carried out the reaction. Now, what we did, we rinse after the experiment, we discard and we rinse with the water. Let's say these are representing the water droplets. And then we fill with a hydrochloric acid, the same amount of a hydrochloric acid, HCl, 25. So even this hydrochloric acid will mix with the water, the amount slightly change, but the number of the moles, because the hydrochloric acid is a reactant here, as addition of the water is not a reactant. So addition of the water will not make any difference to the amount of the moles of hydrochloric acid. That's why we need the same amount. Look, the concentration might change. Concentration is moles over volume, but moles is concentration times the volume. Here the concentration is decreased or the volume is increased, but the moles remain the same. Because we are adding a 25 cm cube of a hydrochloric acid. So this 25 cm cube of a hydrochloric acid and this 25 cm cube of a hydrochloric acid, they will have the same number of the moles. The number of the moles of the hydrochloric acid are not changing by washing a substance with a distilled water. But if you wash a pipette with the distilled water and you don't dry it, or you wash a burette with the distilled water and you don't dry it, that will make a difference to the reaction, but not with a conical flask. Why a conical flask does not make difference to, because that is not changing the mole. But if I fill a burette and I wash the burette with the distilled water and I did not dry the burette, then what will happen? Some of the water is there, the water droplet. And then I refill the burette. So when I refill the burette, now this will have less moles. Why less moles? Because some of the water molecules are there and the remaining is the sodium hydroxide. So if you wash a burette or a pipette with the distilled water, yes, it will make a difference to the reaction. But if you wash the conical flask with the distilled water and you don't dry it, that it does not make difference to the amount needed. Because here the volume is, as we know, concentration times the volume is moles. Here we are taking the same 50 cm cube. So if I'm taking a same 50 cm cube, some water is there. So the concentration will decrease. As the concentration will decrease, the moles will also decrease. But here what is happening? Concentration times the volume is the moles. So as the concentration is decreasing, but the volume is increasing, so the moles remain unchanged. Is it clear? This point about, so there will be no change. Why conical flask is an exception? Look, if you have a conical flask which was having some water droplets, let's say 2 cm cube of a water is there. Example. Okay. And then what you are doing, you are adding a hydrochloric acid from the burette. You're adding you're adding a 25 cm cube of a hydrochloric acid by using a maging cylinder. So what is the total volume of this solution? 2 cm cube water and 25 cm cube of HCl. So what is the total volume? The total volume is 27 cm cube. But this 27 cm cube contain the same moles as without washing it with the water. Like I have a conical flask from experiment 1. I have a conical flask from experiment 1 and I added 25 cm cube of HCl by using a maging cylinder according to the question. So the number, because water is not the reactant here, even though this solution will have a low concentration because of a large volume, but the number of the moles, let's say this was having 10 moles of hydrochloric acid, this will also have the 10 moles of a hydrochloric acid, because the hydrochloric acid, the same volume of a hydrochloric acid is added. But when you're talking about the burette, when we talk about a burette, let's say a burette is there, a burette can maximum hold 50 cm cube. So if I fill a burette, like example, a 50 cm cube of a sodium hydroxide, NaOH, and another example, I first washed with a distilled water. So let's say I wash with the distilled water, some 2 cm cube of a distilled water still left in the burette. Then when I fill it up, I don't have to add 50 cm cube, I have to add 48 cm cube of a sodium hydroxide. So definitely this 48 cm cube of a sodium hydroxide will have less moles as compared to this 50 cm cube of sodium hydroxide. That is why washing a burette or a pipette with the water, yes, it make a difference to the amount needed, but washing a conical flask with the water will never make any difference to the amount needed. Is it clear? So how you score the 2 marks?
Yes.
How you score the 2 marks? First thing you will mention, the amount needed will not change. You can say that because the water is not the reactant or water is not reacting with an alkali, or you can also say that the same amount of acid is added in the both experiments. Like same 25 cm cube of acid is added. So 1 mark is for mentioning no change. 1 mark is for mentioning same amount of hydrochloric acid is used in both experiments. Like we use a 25 cm cube of a hydrochloric acid in both experiments. That's why. Compare the volume of a sodium hydroxide needed to reach an endpoint for experiment 1 and so experiment 1 it was 18.6 and experiment 2 it was 6.2. So what is the ratio between them? So the ratio between them is 3 is to 1. Like 3 ratio 1 is, so 1 mark is for referring a ratio between the two, comparing. And what could be the reason for that? The reason is that it shows like more hydrochloric acid is present in experiment 1 as compared to that in experiment 2. Why the different volume of a sodium hydroxide are needed in experiment 1 and 2? So why we need, so experiment 2 calcium carbonate reacted. So yeah, amount of hydrochloric acid or some of the hydrochloric acid is reacted with calcium carbonate in experiment 2. That's why we need a different amount. The next is calculate the volume of a sodium hydroxide needed to reach an endpoint if experiment 2 was repeated, 0.25 grams of a calcium carbonate instead of zero point 0.5. Look, what we did in experiment 2, we were having a conical flask. We were having a conical flask and we took 25 cm cube of HCl. In this 25 cm cube of HCl, we add zero point 0.5 grams of a calcium carbonate and then we titrated using a burette. We add a sodium hydroxide and how much sodium hydroxide is needed? 6.1 cm cube of sodium hydroxide is needed. Now what we did, we are doing the same experiment. But this time the experiment, we are not adding 0.5 grams of calcium carbonate, we are adding 0.25, half of it. So the hydrochloric acid which is left here will be double of the original one. Like here, which was reacting with the sodium hydroxide, it was reacting 6.2 cm cube. How much sodium hydroxide will be reacted here? So the amount of a sodium hydroxide reacted will be double. Amount of sodium hydroxide reacted will be double of that. Why double of that? Because this initially 0.5 grams were reacting with hydrochloric acid and remaining was reacting with sodium hydroxide. But now we are taking 0.25, so 0.25 is less. So if we have a less amount of a calcium carbonate, so more quantity of a hydrochloric acid or a double quantity of a hydrochloric acid will be left to react with the sodium hydroxide. So the quantity which will be left will be needed to react with the sodium hydroxide. That is like amount of sodium hydroxide that will be 12.4 cm cube. Is it clear? Why it's of 2 mark? 1 mark is for mentioning 12.4 and 1 mark is for mentioning cm cube. Working is not having marks here. 1 mark is for the magnitude, the number, and 1 mark is for the unit. Look, yeah, I will repeat this one. I will repeat this one. If you see the question, in the question, we were having a conical flask. In this conical flask, we were having a hydrochloric acid, HCl, which is 25 cm cube. In this 25 cm cube of HCl, first we added 0.5 grams of calcium carbonate. So when we add a 0.5 grams of calcium carbonate, amount of HCl which is present here will become less. This remaining HCl was reacted with a sodium hydroxide, NaOH. How much NaOH is needed? We need 6.2 cm cube of NaOH, that is in experiment 2. Now they are saying we are repeating the experiment. The same experiment is done. and we are repeating the experiment with taking a small amount like 0.25 grams of a calcium carbonate. So if I use a 0.25 grams of a calcium carbonate, what will happen? The mass of HCl which is left will be, or the moles of HCl left will be double compared to this one. Because here 0.5 grams was reacting with HCl and here 0.25 grams is reacting with HCl. So which, if I compare the number of the particles or the moles, here the mass of calcium carbonate is more. So the moles of hydrochloric acid left will be less. Here, mass of calcium carbonate is less, so the moles of hydrochloric acid which will be left will be double of the first experiment. Like greater number of moles or greater number of the particle of HCl will be left. Yes, the amount of HCl is decreasing because it was reacting with the calcium carbonate which was added first. So now, because less quantity of a calcium carbonate is added, so remaining will react with the sodium hydroxide. So here less quantity of HCl, so 6.2 was reacting. Here we have more quantity of HCl. So how much is needed? We need a double of it because 0.25 is only reacting with HCl. So remaining amount is reacting with sodium hydroxide. So if this was 6.2, this should be double of it. So it will be 12.4 cm cube. Describe how the reliability of a result obtained could be confirmed. Whenever you want to check the reliability of the experiment, like example, specifically for titration experiment, you should always mention repeat and until the results are concordant. Repeating it, plotting a graph is not the right term here because we don't have this much set of result to plot a graph. Even repeat the experiment until the results are concordant. Whenever titration experiments are there, you always look, this is right statement as well, but you repeat the experiment until the results are concordant. Concordant, when I use the term concordant, it means they have a difference of zero point 0.2 cm cube. So repeat and compare the results until two results are concordant. Concordant, like example, if we did the first experiment, let's say the first experiment, the value was 6.2. The second experiment, we did the value was 6.6. So we have to do it again because they're not in the range of zero point 0.2. Then we did again and we got the result as 6.7. So now two results are concordant. So I will take these two results. So for titration, what is to check the reliability of the result, what should be the mod? How you should check the reliability? Repeat the experiment until and compare the results until two results are concordant to 0.2 cm cube. Is it clear, this one? Question 2.
Yes, sir.
In which scenario do we in which scenario we plot a graph when you're collecting a temperature, when the experiment is there about the temperature change, measuring a temperature change, you should mention plot the graph. Like when you have a series of result, plot the graph. When you have like a one set of one value for each experiment, then we check without the concordant results. So use the same link to join again. We'll discuss the remaining of this paper.